So we just saw that adding the gradient to the current x position to get the new x position didn't work well. Let's try backing off a little bit from that idea and say, well, maybe we'll add 50% of the gradient or 10% or something. And that idea of multiplying the gradient by something is called the learning rate, and it's often denoted as alpha. And so we'll just say there's something we'll multiply it by. Maybe this will take care of the units problem too, because maybe alpha has the right units to make the units match between this term and that term. That's not quite true. The story is deeper than that, but we'll get to that in a later video. So I've got a new function I'm defining here, steepest descent 1, to go with idea number 1. And it has a parameter called learning rate. And it's all the same as before, except here it multiplies the learning rate by the negative gradient, and that's our update. And here let's try a learning rate of 0.1, so 10%. Let's try that. And let's take a look at the function values. It started at like 10 to the 1, and then it was 10 to the 2, and then it was 10 to the 3, and 10 to the 5. This, again, is not doing a good job minimizing, is it? In fact, Python is giving us overflow errors. Apparently we went past the largest number it could reasonably represent. So maybe we'll back off a bit. Let's try 0.3. So I'll run that. Oh, now it's starting at 11, then going down to 8, 6, 4, and then the final value after 500 steps is 10 to the negative 6. That seems pretty good. We generated this data, so the regression data, so it falls on a perfect straight line. So the true optimum objective function value should be 0, a 0 mean squared error. So this feels like it's getting pretty close. Maybe we can investigate what the coefficients are doing. They seem to be, I mean, they're bouncing around a little bit, like 0.19, 0.04, 0.18, 0.07, 0.17. But the final value here that we're doing this way seems pretty close to the 0.75, 0.50 that we know is the optimal intercept and slope. Let's go ahead and graph it. And we started at 0, 0, and then apparently we bounced around a lot, but then kept bouncing around not quite as much. And just to keep track of time here, I've plotted a red plus sign at every 100 iterations, which we'll also call epochs later. So you see in 100 iterations we got from here to there, and then in another 100 iterations didn't get quite as far, and then another 100 didn't get even quite as far, but we ended up in a pretty good position. What could we do to improve things? Well, we still seem to be overshooting kind of the bottom of the valley and going up the other side of the mountain on the other side of the valley. Maybe if we backed off even more from that gradient, had a lower learning rate, maybe we would get closer to the bottom of the valley on that first step. So let's go change the learning rate. Let's try 0.01, and we'll rerun it. And again, we seem to be converging fairly well. Let's look at those coefficients. They didn't get toward that 0.75, 0.50 like we saw before. Let's plot what's going on. Okay, so that first time we didn't go kind of all the way across the valley and up the other side. We didn't even get down this part of the valley. And then we did kind of get toward that, that bottom of the valley that runs this way. But apparently, since our learning rate is smaller now, we're taking smaller steps. We're not getting as far along the valley this way as we take steps. So 0.03 zigzagged a lot, which is, we don't like overshooting things if we don't have to. 0.01, we apparently could have done a little bit better and gone a little bit farther on each step and gotten to the optimum faster, hopefully. So here's the big vocabulary word that we're introducing right now. This learning rate is called a hyperparameter. The parameters of our model here are the slope and intercept that help us predict the y values from the x values. So the same things you would usually call parameters in a statistical model. But the learning rate is not part of the model that helps us predict y from x. It's just something that helps the optimization go faster or at least not diverge. So hyperparameter, that's the big new word. It's something that helps the optimization, but isn't part of the model that we're trying to optimize. Another way you can think of hyperparameters is if you tune the model using this learning rate or that learning rate, and you get a slope and intercept, you can hand that slope and intercept to someone else. They can use it to make predictions of the y values from the x values, and you don't have to tell them what learning rate you used for them to be able to use the model appropriately.